Hello, everyone. Can you hear me? Thank you. Okay, so today we'll have a look on query processing and evaluation, how to evaluate a query. First of all, the assignment 1 analysis. Most of you are in this region from 51 to 75%. Around 10 to 12 group was greater than 75. The average score was 57%. Last semester it was 61%. It dropped down a little bit. Yeah, hopefully assignment 2 will be better for you. Okay, and acknowledgement of the country. So I would like to acknowledge the traditional owners of Australia and recognize their continuing connection to land, water, and culture. I am currently on the land of the Burra Matagal people and pay my respect to their elder, past, present, and emerging. I further acknowledge the traditional owners of the country on which you are on and pay respect to their elder, past, present, and future. It's a reminder that there will be a quiz next week. Okay. Quiz 2, the last quiz of this unit. So the quiz will be released like quiz 1. It will be released on Thursday after the tutorial session. Okay, so at 9 p.m. And it will be due on Friday at midnight. Quiz duration is 1 hour. Only one attempt is allowed. Question structure will be similar to quiz 1. There are 10 MCQ questions and 3 essay type questions. Okay? And it will cover content from week 6 to week 11 without week 7. Okay. So week 7 will not be covered, like I said. So 6, 8, 9, 10, and 11 is today what we're going to learn. 10 MCQ questions and 3 essay questions. You're familiar with the structure. Okay. So these are the 5 topics that will be included: integrity constraint, transaction, normalization. Last week we learned storage and indexing. And today we'll have a look on query processing. Okay, so what is it that we are going to have a look? So today we will have a look on query processing, how query is processed. Okay, what happens internally and what sort of algorithm do they use in there. So this is the internal architecture of an DBMS. You are already familiar with this architecture. We have seen this one again and again, almost in every week. So today we are looking into this part where we have parser, optimizer, plan executor, and operator evaluator. Okay, so we had a look on application development. We learned about SQL. We learned about transaction locking. Last week we learned about disk management, right? So we only didn't cover recovery manager. We'll leave it at there. So today we'll cover this, and hopefully this whole architecture is complete then. So yeah, so here you can see there are 4 parts: parser, plan executor, optimizer, and operator evaluator. So that's what we're going to have a look. What is the functionality of each of these? So the first step of a query processing, we write a query and we see the output, right? So we write a query and we get the output. So what happened inside? That's what we are going to have a look today. Okay. So the first step is, after writing query, it goes through a parser. So parser does the parsing and translation. So translation simply means it converts that query of yours into a relational algebra expression. Okay, so that is the job of parser. So we have idea about query, we have the idea about relational algebra. So from a query, the parser first checks. So parsing simply means check everything, whether the syntax is correct, the table that you are trying to access, you have access to that table. So all of those things, all of the syntax error that we see, that you have missed semicolon or the syntax is not right. So that is the job of parser. So parser checks the syntax, and if there is some issue, it complains to us. So it verifies everything and then it translate that query into relational algebra expression. So we know about relational algebra expression, so that's what it does. Okay. So if you have views, if you remember views, so inside a view there is a query, right? So that we save as a view. So if there is a view in your query, so this parser will also convert that or rewrite that view into the actual query that we have inside that view. Okay. So all these translation are the job of this parser. So parser will do that for you. So after everything is fine, parser simply returns an relational algebra expression. That relational algebra expression comes to the optimizer. So what is the job of the optimizer? So optimizer will do the optimization. So there will be a lot of plans how we can execute and query. Okay, so today we'll have a look on different algorithms, so different process. Okay, and among all of those plans or among all of those algorithms, the optimizer will try to figure out which one have the lowest cost. So which one is the optimized one for this query. Okay, and that is the job of optimizer. So optimizer will return an execution plan. How we should run this relational algebra expression that we have. Okay, so which algorithm we should use in which step. So that's what this execution plan is. And that's what we are going to learn today. After that execution plan is finalized, this plan executor, the name says that it will execute the plan that we have, the operator evaluator, if we have any operator there, so that will be evaluated. So all the evaluations will happen in here based on the plan. Okay. And it will execute the plan and return the final output that we are expecting. Okay, so that's what every bit does. First, we write a query. Parser checks everything, whether everything is fine. After that, it converts that one into a relational algebra expression. Taking the relational algebra expression, optimizer try to figure out which algorithm should it run. Like last week, we learned about different searching algorithm like binary search, linear search, index search. So which searching sort of thing we need to learn, or today we'll have a look into different algorithms for joining, for sorting. Okay, so which algorithm is suitable for this case? That's what optimizer will figure out. From there, it will return an execution plan, and plan executor will simply execute that plan. So plan executor needs to have access to the actual data. It will go to the actual data, then it will apply this plan, and then to figure out the actual output that we have. Okay. If you have remembered view, so that's why I just included this one here again. So hopefully everyone remembers view is nothing but a virtual table. So inside a view, there is a query, right? So we can use a view as a table in other queries as well. So view, we can simply think about that as a table. Okay, so and we can use a view how we use a normal table, right? So it is normally evaluated on each use. Every time you run a view, like select something from a view, so internally what happens is that view runs, right? The query that you have saved for that view, that one actually runs. So, and that's how you get the output of that view. Yeah, so let's say we have a query like this, we know how to create a view. So we write the command create view, then any name of the view that you want to keep, and then this as keyword that you use. Okay. So next time, if we want to use this view, we can simply use this one as a table name, right? So how you use a table name, employee hired date in the from clause. So there we can use that one. So previously the parser we have seen. So parser jobs, when I write a query like this, they select everything from employee hired date, order by last name. So this is a view, right? So this view will be changed to this actual query. So that is the job of the parser as well. Okay, so parser will rewrite this query, convert it into this, and then it will convert it into a relational algebra expression. Yeah, so going into more details or giving you an example in here. So let's say we have a query like this, select name from this to table, where we have a condition into a static code equal to this one. Okay. So like we learned, parser will try to figure out whether everything is syntactically correct. If everything is correct, then parser will return a relational algebra expression. Hopefully this part is making sense. So here we can see a query, tree like a structure. But when we learned a single line. I will explain this tree, don't worry. So here we probably can understand what is happening. So here we have a student table and enroll table. In enroll table, we are putting that condition first, right? So based on that condition, few rows will be selected from enroll table. Then these two will be joined in here, and from there we will only select the name. So that's how a tree-like structure works. So this is what this parser will return. Then the optimizer will try to figure out in each of these step or each of these step which algorithm it should use. Okay, so let's say to get all the data from student table, it will use index scan, let's say. Okay, so last week we learned about linear search, binary search, index search, or index scan. So think about it will be able to use an index scan. In here, it might use table access. Table access simply means unordered data. So that one simply means linear search, right? Here we can have index search based on some criteria. So this is the main thing, that it will figure out all of these details, that which algorithm should we use depending on the algorithm, depending on the query that we have. Here we can see nested loop. So that is for join. That's what we are going to learn today. So don't worry, if you don't know nested join, that's what we'll learn today. What algorithm should we use for joining? Okay. So one of the algorithm is nested loop. Okay, so you can use nested loop or block nested loop or other algorithms, and from there we'll simply project. So here you can see the job of optimizer is to try to figure out which algorithm or which process we need to use in every step from the query. After that, plan executor will get access to the data, right? Based on this algorithm, it will simply apply all of those algorithms, take the data as an input, right? And then finally figure out what will be the output there. So let's go all of these one by one. So first part is this tree-like structure, right? So this tree-like structure is known as expression tree. When we show a relational algebra as a tree, so that one is known as expression tree. Okay. So operator have one or more input set and return one output set. Operator simply means, let's say here join is an operator, right? So here we can see two input for this one, that this join will happen between student and whatever the output on this side. There will be an output, so output simply means whatever we return to this upper level. Leaves correspond to the base case. So in a tree, if you have some idea regarding tree, so this last node that we have, last node means where there is no other children. So these nodes are known as parents. So first, let me draw a few things. Yeah, so this one is normally known as the root, which one at the top level of a tree. So normally that one is known as the root. Okay, that is also a parent because it also has a child. And all of these internal nodes are known as parent. So here, this one is a parent. This one is also a parent because this one has a child in here. So these are normally termed as child. Okay. So the node that has no other child in here, there is no other child. Right? So these are known as leaf node. So student is a leaf node, enroll is a leaf node. Okay. So that's what is written there. The leaf node are normally the normal table that we create. Okay. Okay, so that's what is written here. Leaf correspond to the base tables that we have in our database. So hopefully you can create an expression tree, not that difficult. Like the example we have just seen, if you have a query like this, the relational algebra would be something like this, that where first we put a condition on the enroll table, take everything that we have based on this condition, and then join from student table. First question is, can we simply put this condition on top of a student? What do you think? Not in here. Can we put that one in student? In the chat box, there are some questions. Sorry, I missed that one. Few comments regarding the marking. What if the assignment marker does not reply my email for clarification? Try to remind him one more time. Okay, even if after that they didn't reply, let me know. Okay, I can remind them as well. Are we gonna have a sample quiz? No, for second quiz, there is no sample quiz for quiz 2. Okay. You are already familiar with the system. You already know the question structure. Okay. So anyone have any idea what I asked in here? So rather than putting this condition on this side, can I simply put that on top of a student? Hopefully you remember the structure of a student and enrolled. So student table have the student's information like student ID, student name, email, sort of thing. Enroll have in which courses they are enrolled. At least one person replied no. Any reasoning why? Any reasoning why this one is not possible? Someone is saying that slide downloaded from Canvas is quite different from the one on screen. It should be the same. I'll have a look again if I have uploaded the previous one, but it should be the same. But I'll check again, don't worry. Yes, so some of you said student does not have unit of study code. Yes, so in the student table, we don't have this, right? So that's why we will not put that condition on this side. So only in enroll table, we have student ID and unit of study code where he is enrolled. So that's why we're putting the condition in here. So that's what I just wanted to mention. Okay, so we know the similarity between these two. So select is simply a projection of relational algebra. When we have a join, so that's what is written in here. So this is a join. On the left-hand side, we will have a student. On the right-hand side, we have enrolled based on this condition that we have, right? So this one is the selection. Hopefully all of you remember. So this one is known as projection. In relational algebra, this one is known as selection. Hopefully everyone will be able to create this expression tree if needed from a query. So that was the first step of parser. So parser will return this tree. Next step was the optimization. So based on all of the plan that we will have, we will try to figure out the optimal plan. Someone is asking, do we need to draw it for the quiz? No, you don't have to. What was I saying? So optimization, yeah. So in the second step, the optimizer will try to figure out an optimized plan, right? So based on all the plans that are available. So here you can see that it will first figure out the tree plus the choice of algorithm for each operator. So like we have an join, we have a selection, we have a projection for each of those. So which algorithm should be there? Okay, so that's what this optimizer will figure out. Find an optimal plan among a set of all the equivalent plans that you have. So here optimal simply means, last week we learned that simply means that the input output cost that we are going to have. So whichever plan have the lowest input output cost, we'll simply choose that one. But don't take too long choosing a plan. If your time to choose a plan is greater than the time of actually executing that algorithm, then that is not right, right? So if you are taking, let's say, 10 seconds to choose a plan, but to execute a algorithm, you simply need 2 seconds. So too much overhead will be there. So don't take too much time to choose a plan. Within a short period of time, whatever the optimal is, you can simply return that one and run that one. So that's what the idea is. So in the query execution plan, so what sort of plan we are looking into? So let's say we have an expression tree like this, very simple, that from account, put this condition, whatever rows are returned from there, simply select the balance. Okay. So in here, let's say account table is unsorted. Okay. So that simply means that we can only apply linear scan in there. So we will have to apply linear scan and then filter out all the rows which does not satisfy this condition, and then finally we have to project, right? Only the balance thing we have to print. This could be one, or let's say we have access to the index. So we are looking into balance and we already have an index created based on balance. So if that is the case, we definitely can use index scan, right? So index, this one is range query. So index range scan we can use, and there we can pass all of this. And based on that, we can simply project. So here we have two plans, right? So first one is based on linear scan. Second one is based on index, let's say. So we'll try to figure out the cost like we did last week, okay? Based on the cost, we can determine which one will be optimal. So that's what this part will do, that they will always figure out the plan with the optimal cost. So whenever we are looking for the optimal plan, right? So last week we learned about access path. Access path simply means which data structure, which algorithm we need to use, right? So we are familiar that if it is a heap file means unordered data. So that time we simply have to use linear scan. Different names are table scan or file scan. If we have an index available, then we can definitely use index scan. From last week, we learned that index must match the search key, what we are looking for. The index will be based on that one, right? So if we have an index on different key, then that index is useless. So if we have an index based on student ID, but we are looking for, we have a query which is based on student mark, then that index will not be helpful. So we simply have to remember that. Yeah, so today we'll have a look on different sorting algorithms, but before going there, just want to clarify one thing. So we know, or we learned that when we have a query, right? So normally a query does not remove the duplicate. So we always get the duplicate as an output. Anyone remembers what I have to do if I want to remove the duplicate from a query, from the output of a query? Distinct, yes, that's right. So the question is why query does not remove those duplicates automatically? Why we have to force the system to do that removal by writing a keyword called distinct, okay? So the main thing is that removing the duplicate is very expensive. So when we have millions of data, from there we want to select, let's say, student ID, but we only want the distinct data, right? So at that time, how can we remove those duplicates? So that's the thing, right? So if, let's say, this is the data I currently have, and I got 10, I want to check whether 10 is duplicate or not. Okay, so how can I check? First of all, think about this unsorted data. So if it is unsorted data, then only option we have is to compare 10 with all of these, right? So now think about, I have millions of data. After that, I got millions and one, right? So what I have to do, I have to compare it with all of these previous data, millions of data I need to compare. Because in linear search, we only have option to compare with all of those, right? So let's say somehow I compared everything for 10. Does that help if something else comes up? So if 13 is there, I just checked all of this data, right? But does that help? It certainly does not, right? So because we don't remember all of this data. So when 13 comes, again, we need to start from its immediate data and compare with all of those, right? So we are scanning the same file again and again. Think about how many IO costs you need to transfer all of these files from hard disk to main memory. To compare, you need to transfer everything, right? So that's why it is written that removing duplicate is very expensive, okay? Unless you specify that I need distinct data, query automatically does not do that. But if you say distinct, or if you write order by, right? So when we write order by, we want the data in a particular order. So at that time, query has no option but to order the data, right? So even if we have sorted data and there we are trying to remove the duplicate, same thing will happen. when we have a new data, we need to figure out whether that data is there or not, right? So if the data is sorted, we definitely can apply binary search to figure out whether 10 is there or not, right? But again, last week we learned that keeping the data in a sorted format is very expensive. So if I want to insert a data, I always need to figure out what is its best position, right? And then put that data in there. So, and that part is always very expensive. So that's why query does not automatically remove the duplicate. But if we apply distinct or we write like order by, at that time, data have to be sorted. Okay, so data have to be sorted. So what sorting technique can we use to sort the data that we have? That's what we're going to learn. Just before starting to learn about algorithms, one other thing to clarify is that when we have an expression tree and we figured out all of those algorithms, okay, so now how should I evaluate? What should be my process? Okay, so if you remember in that tree, we have figured out all the algorithms, let's say, okay, so I run the algorithm, I get an output, right? So based on the output, how should we get the final output from there? We can think about two approaches. First one is evaluate one operation. So let's say I have a tree like this. Here I have something in the both side, I have some data. So whatever you have in here, evaluate that. Okay, so let's say I have a join in here. A join in here. Okay, so join simply means I will join these two tables. Let's say this is student table, this is enroll table, right? So once I join, I get a bigger table, right? Or the smaller table, but I get table as an output. Where should I keep that table? Right? So I need to store that table in here and then push that table on the top of its current level. So we'll push it to its parent, and there we might have some other operator that will be evaluated on that. So that is the first step, is that simply evaluate one operation at a time. Result is stored in a temporary relation for subsequent use. Or whenever we need, we can simply use this one. Second is pipelining. Pipelining simply means evaluate several operations simultaneously in the pipeline. So that simply means that we will perform some operation in here, we will perform some operation in other part of the tree as well, if possible, and then we will try to combine all of those. Okay, I'll explain more. So materialization is the simplest one. So think about this tree. So here I have account, customer. First condition is that check whether balance is less than this one or not. So what can we do? We definitely first check this condition on this account table. Okay. So the data becomes less. So we had all of these pages. So we now only have 3 pages and we stored them in here, right? So next time for this join, I need to push. So I will send all of these pages in here, and this customer will come in here, customer data, then we'll join and we'll again store the result. Okay. Now the question is, what do you think, where will this data be stored? This intermediate data that we have. So these are not actual data, right? These are intermediate data for calculation. These are the actual data, account, customer. So where will we save this data? Any idea? Where simply means here primary memory, secondary memory. Where should we store this data? In primary memory or in the secondary memory? Anyone? Yep, someone says secondary, I guess. Yep. Someone said temp, yeah, temp, but where the temporary data will be stored. Yeah. So first of all, we can think that, okay, we might store that one into RAM, that means in primary memory, but if the resultant data is too large, right? So, and it doesn't fit in the main memory, then what do we have to do? We have to push it into the disk in the secondary memory, right? So now think that we are pushing this intermediate data into the disk as well. So what does that mean? That simply means that the time to get the output is increasing. So every time we push something in the disk, and later when we want to use this one, so what do I have to do? I have to take this data from secondary disk. So this is secondary disk to main memory again, right? So what does that mean? So that simply means we are increasing IO cost. So if we are increasing IO cost, that is the cost, right? So we always calculate. So that simply means that this approach will have a huge cost compared to the next one that we are going to learn. Hopefully this part is making sense. So once again, we're storing the result temporarily. Where can we store? If it does not fit in the primary memory or main memory, then we have to push it in the disk, which is usually the case. So we push it in the disk, and then next time when we need that data, we get the data from disk again. So that simply means that we are introducing new input-output cost in here. But the advantage is that we can always apply. It doesn't matter which type of query we have, what type of table we have. So we can always apply materialization, right? So we can apply this technique that will simply apply this condition, whatever we have, we will store and then we'll push it forward. Okay. But like I said, cost will be much more higher. Why the cost is higher? Because we have to store. So can we figure out a way so that we don't have to store anything? Someone is saying store on disk, not memory. So disk is a memory, right? So disk is a secondary memory. And other one is the main memory or RAM that we have. Okay. Yeah, so if we figure out a way so that we don't have to store anything, that would reduce that cost. Right? So that's what pipelining is. So in pipeline, we perform several operations simultaneously and pass the result of one operation on to the next. We keep doing that. So here you can see that I'm not storing anything in this state, right? So then how this one will be evaluated? So think about first, I run this query or run this condition on this table. So I will get row by row, right? So first I will take one row. I'll compare this condition. Does this row satisfies this condition? If yes, then I don't want to store this one. I want to push it forward. So that's what we can do. So let's say T1 is my tuple one. Tuple simply means a row. So I figured out that T1 satisfies this condition from here. So what we can do, rather than storing T1, we can simply push it into the next level, right? So if T1 goes in here, based on T1, we will perform this join. Okay, so we can simply have a table where I have only one row. I perform a join with customer, and whatever the result I get, I push it forward. Okay, so that's what we can do. Rather than saving, whenever I am getting a result, I'll push it forward. So let's say I have another tuple T2. Again, I'll simply push it, and then we will go to the top. Okay. Will this be cost effective? What we are increasing? We are increasing the processing, right? So previous approach was that we are saving everything. That simply means that we are getting all of the rows at once, and then we are performing join only once. But this time what we are doing, for how many tuple we have to perform this join that many times. So which one will be beneficial? So here we are performing number of extra joins. Okay, let's say I have 1,000 tuples, so I have to perform join 1,000 times compared to the IO cost that we have in here. So in one side I had IO cost, right? In another side I have processing time. because I have to perform join again and again. So this is what I'm increasing, right? So these are the two that I'm increasing. Which one will always be higher? What do you think? IO cost or this processing time? Yep. Yes. Yes, someone wrote the reasoning as well. The CPU processing should be quicker than IO, definitely, right? So here we are performing operation on CPU. So here we are performing this operation on CPU, but in here we are doing some disk operation, right? So we know disk operation is always much more slower than CPU operation. So in this case, IO cost will always be higher than processing time, right? So this processing, although we are doing the same thing essentially multiple times, right? But still this time will be less than the disk IO time that we will have. So that's why pipelining will give us better performance. Okay? So that's why it is written that much cheaper than the previous one on materialization. Materialization simply means save everything that you have. Okay. Because we don't need to store it into a temporary table to disk. Does this make sense? Any question on these two? Everyone is very quiet today. Feeling tired, everyone? Yep. End of the semester, I understand. We only have two more weeks, so all of the deadlines are there. Yeah. Okay, just try to stick around. Okay, this thing will pass. Okay, so we have covered the first part. Someone is asking, can assignment due date be due on Sunday? No, that is not possible to extend. Someone is saying, so pipelining don't save the intermediate results. No, it doesn't. Okay, so whenever it gets the result, it push it into the upper level. Okay, so in every step, it simply calculates. Once it gets the result, it push it. Okay, so it will not save anything. That is the benefit of pipelining. Okay, so those are the basic steps in query processing. Okay. Those 4 steps that we had. So we will learn about sorting today. Anyone knows about any sorting algorithm? You can write name as many as you know. Someone said pipelining evaluation always better. Yes, theoretically that will always be better, right? But depending on how many data you have to save, sometimes materialization could be better. If you have very small data you can feed in the main memory, that time it could be better, but theoretically pipelining will always be better. Okay, so I was asking about sorting algorithms. Anyone knows about any sorting algorithm? Bubble sort, quick sort, merge sort, decision tree, quick sort, bubble sort. Okay. Anything else? Heap sort. Heap sort. Anyone else knows anything that has not been mentioned in here? So far we have mentioned 4 or 5. Bubble, quick, merge, decision tree, heap. 5. Anyone knows anything else? Any other sorting technique? Is hash map is sorting method? No. Anyone knows about bucket sort? Yeah, someone just wrote bucket sort. Yeah. Bucket sort, radix sort. Excellent. Yeah, you know a lot of algorithms. That's great. Insertion sort, selection sort. That's great. Yeah, so if you're not familiar, don't worry. We'll only talk about only one sorting algorithm today. Okay. If you are willing to learn about multiple sorting algorithm, you can have a look on that web page that I have shared with you last week. right? So I hope that you have this link. So here there are a lot of sorting algorithms. You can have a look. Okay. So let's say bubble sort, how does it works? Yeah, this one will make sense that you don't compares, then changes the value, those sort of things. Okay. You can have a look, but today we'll only talk about one sorting algorithm. Why? First, let's try to figure out. Yeah, so importance of sorting. When do we need sorting? When we specifically call for order by, or let's say distinct, at that time we might have to apply sorting technique. All the sorting techniques that you have mentioned, which one is the best? We have learned that quick sort is the best, right? So that's what, based on the running time, we know that quick sort is the best one. But the problem is quick sort only works when all of the data fits into the memory. If the whole table does not fit in the memory, then quick sort cannot work in there, right? So quick sort needs all of the data. So let's think about, I am trying to sort the data, millions of data. Do they fit in the main memory? If yes, then yes, we can apply quick sort. If the data doesn't fit in the main memory, then quick sort will not work. Okay, so at that time, we might have to think about another technique. So where quick sort might not work, think about when we have 10 GB of data we want to sort, but our RAM size is 4 GB. So we cannot store everything at the same time. At that time, quick sort will fail, but still merge sort will work. And this one, because we'll be using this one again and again, this one is known as external merge sort. Why external? I'll explain later, but hopefully you are familiar with merge sort. And this one will be known as external merge sort that we'll have. Okay. If someone is not familiar with merge sort, I'll try to explain so that the next thing makes sense. So merge sort, pretty easy. First question, is this data sorted? That you can see on my screen. Is this data sorted? Should be very easy to answer. No, definitely not, right? This data is not sorted. But have a closer look now. If I divide this data into two parts, okay. So if I divide this data into two parts, let me draw in here. Is this first part sorted? Yes. Is this second part sorted? Yes, right? So that's what the idea of merge sort comes from. If I have two lists which are sorted, then what can we do to sort the whole thing? Okay, so that's what merge means. Merge means we want to merge more than one thing, right? So we want to combine more than one thing. So I have two lists. Think about this one part is sorted, this part is sorted. How it will make sure this part is sorted, we'll talk about that. Don't worry. For the time being, just assume first part is sorted, second part is sorted. How can I combine these two? That means merge. How can I merge these two so that everything becomes sorted? That's what we are going to do. Okay, so that part is known as merging. So let's learn about that part first. So first we divide the data into two parts, right? So from the color you can understand this one is left half, this one is right half. Okay. So how can we sort the whole thing? So simply comparing two things, the first element of the first list and first element of the second list. So if I simply compare 1 and 6, I can say 1 will be my first element in the ultimate sorted list. Does that make sense? So if I simply compare 1 and 6, from there I can say that since 1 is less than 6, 1 will be the minimum element of this whole list. Why? Because I don't need to compare with 1 with 18 or 1 with anything else, because I know this list is sorted. Since this list is sorted as well, so if 1 is less than 6, then 1 is less than all of its elements. Right? So that's what the assumption is, that this list is sorted. So we simply compare 1 and 6, and based on that, we say 1 will be my first element in the ultimate sorted list. Okay, so we put 1 in here. So 1 is gone, 1 is not here anymore, it is in the new list. So what do I have? Again, I will repeat the same process. I will simply compare the first element with the first element of this remaining list that we have. Okay, so simply compare 6 and 9. Since 6 is less than 9, we know that 6 is the next minimum from all the element that we have. So we simply take 6 from there and put it in here. So I now have a list like this and this. Again, repeat the same process, compare the first element with the first element. Okay, so repeat this process again and again. Hopefully that part is making sense. So I'll compare 8 and 19, 9 will come. We'll compare 15 and 18, 15 will come. Then we'll compare 43 and 18, 18 will come from there. Then we'll compare 56 and 43, 43 will come from here. Now you can see that this list is empty. Once I put 43 in here, then this list is nothing is there. This one is empty. Do I need any other comparison to figure out which one should come? Definitely not, because I know that all the elements in here are sorted. I can definitely simply put all of them in here without doing any comparison. Right? So I can simply put 56, 62 in here and everything will be sorted. So few advantages, just comparing two things, we can figure out which one will be the element I need to put in the main list. And once one list becomes empty, we can simply copy everything from the other list and put it in the final list, right? So we don't need any comparison there. Hopefully this part is making sense. So this one is known as merging. So now you can see that once we have two lists which are sorted, we can merge them into a final list where everything will be sorted. Now the question definitely comes to mind is, how do we ensure that this list will be sorted? This part is sorted, this part is sorted. How do you ensure? How can you say that? So think about for which list you can say that that list is sorted. For which list you can say that that list is always sorted. When I have only one element. If in a list I have more than one element, then I need to check whether that list is sorted or not. If in a list I have only one element, is the list sorted? Yes, because there is only one element, right? So start from there. So that's what the idea is for dividing. So we have a lot of data, that's fine. We don't care how much data we have, but think about this theory that when we have only one data in a list, that data is sorted. So what we will do, we will simply keep dividing this data that we have, unless we have only one data in each list. So divide this data. So let's say we are dividing in the middle, right? So if I'm dividing in the middle, so first part will have these 4 data, second part will have these 4 data. Again, I don't know whether this one is sorted or not. So do that process again. So divide this data, divide this data. Again, I have more than one, so I don't know whether that is sorted or not. So divide that one. Now think about, forget everything, simply think about this part. In here, I have this one, this is a list, this is another list. Are they sorted? Yes. Since they are sorted, these two are sorted list, I can apply that merging technique that we have just learned to sort these two, right? So we can apply all of those in here, then we can keep going up to do that thing. So that's where conquer or merge thing happens. So first we divide everything into single element, then we start to combine. So we take 2 at a time, right? So we take these 2 because this one is sorted, this one is sorted. The technique that we learned, using that one, we can simply have this one, right? That's why you can find this. Now we know that this list is sorted, this list is sorted. If that is the case, we can again apply that technique and combine these two to figure out the final list. Now can you see that we had 8 elements and now we have 2 lists where this part is definitely sorted, this part is definitely sorted, right? So if that is the case, we can simply combine these two and put it into a final list. Any question? That's it about merge sort. So first divide everything unless you have only one element in each list, and then you try to merge using that technique. Any question on merge sort? Yep. So same thing will happen if the number is odd, how to deal. So think about, I have 1, 3, and 2. So these are the 3 elements that you have, right? So you'll divide it into 2 parts. Let's say in one side I will have 1 and 3, in the other side I will have 2. I'll divide it into 2 parts. Here I will have 1, I will have 3, right? Then I will start to combine. So first I will combine 1 and 3. I will get 1 and 3. So this is a sorted list. I have 2, that is the sorted list. Then I'll combine these 2, and from there I will get 1, 2, 3. Hopefully that is making sense. So in here, everything is nice. Everything has 2 elements, but in here, something might have only 1 element. So we'll combine when the other part is sorted. Does this make sense? Anyone have any other question? Main thing, remember, first divide and then merge everything. Divide and conquer, we say sometimes. Can we take a break? I'll give you a break, okay? Not now. Someone is asking, do we need to know all of these algorithms work for the exam? You don't need to know the algorithm, okay? How the algorithm works, what is the running time, you don't need to know that. But I still wanted to tell you how merge sort works so that the next thing that I'm going to show you, that makes sense, okay? So the next part you need to remember, not this one, is external merge sort. That part you need to remember. Okay, so how we are going to sort the data that doesn't fit in the main memory. Okay, so now we have this idea about merge sort. From there, think about, I have these 6 blocks of data in the disk, that means in the secondary memory, in the hard disk. In the main memory, I have a space only for 3 blocks. Okay, so how we are going to sort this data? Since we learned merge sort, right? So merge sort says that you can divide the data into multiple parts, sort each of the part, and then combine, right? So that's what we have learned. So that's the technique that we are going to use in here. So since we can only store 3 blocks, but we have 6, what first thing we can do, we can divide the whole data into 2 blocks, right? So R means this is the first run. So in here I have 3 blocks, in here I have another 3 blocks. So what I can do, I can simply take these first 3 into main memory, run the sorting algorithm and sort that one and push it back, right? So that's what we are going to do. So we'll take only these 3 blocks, load them into the main memory, then sort them, okay, using the technique we learned or any technique which is available to you, and then push it back. Again, do the same thing for the next part, right? So take this part, make it sorted, and then push it back to the disk, right? So how many run like this do we need? Definitely how much data we have and how many buffer space we have in there, right? So that's what the first thing was written there. Let me show you, I skipped a little bit, is this one. Is that how many run do we need? Definitely how many data we have. So we had n number of block, okay? And then how many block we have in the main memory. If we divide that to, then we get how many run do we need. So in here I have 6 block, but in the main memory I have 3 blocks. So definitely I need 2 runs to make them sorted, right? Individually. We have not sorted the whole data, but individually to sort them, we need to have 2 runs. Someone is saying, there is nothing when we put it into memory or we do not care. Yes, there could be something, that's fine. So think about these 3 are the available space. In main memory, there could be 10 blocks, right? So other 7 blocks are used for something else. So right now you have 3 blocks empty, okay? And there you are copying all of this data and doing all of this operation. Okay. Yeah, so that is the first part, that take everything into the buffer space that you have and then make them sorted. After that, I want to sort the whole thing, right? So what do we need to do next time? Which part do we need to take and make them sorted? Can anyone guess, or can anyone just see from this data which part we need to put into the main memory to make them sorted? Someone is asking, can we scale that up to large data like 8 GB needs to be divided to 2 feed into 8 GB RAM? Yes, that's what exactly I'm talking about, right? So how much data you have and how much in the secondary memory and how much data you have in the main memory. We'll divide that one, okay? And then we'll put that one in the main memory and perform that one. Yes. Yeah, next time, which one should we take? Yep. Now you got that idea from merge sort, right? So we simply need to compare the first element of each of the list, right? So take the first element. So you can think it like this, that first we sort it this way, all the rows. Now we are going to sort all the columns. Okay, so that is another way to remember how it works. Or if you remember merge sort, you know that we simply need to compare first element with the first element from here. Yep, someone is saying we need an extra area for this implement or no? Yes. So that's what we are going to do. So we'll take these two, right? But we need an output buffer, because when we compare 1 and 2, let's say I'm comparing 1 and 2. So based on these, 1 will be lower than 2. So I need to put 1 into the main list, right? So that's why this one is known as output buffer. So this will be the list where I will put that one. Okay. So first of all, I'll put 1 and 2. Okay. Again, I had 1 and 5 in this block. In this one, I had 2 and 22. First, I will take 1, right? After comparing 1 and 2, then I'll compare 5 and 2. And then I'll get 2, so I'll put it in here. So in a block, I can have only 2 data. So that simply means that output buffer is full. If output buffer is full, then we cannot compare 5 and 22 and put any data in here. So what can we do at that time? When output buffer is full, we have to push it into the disk. So that's what we are doing. Now we have got some space in here, right? So we'll compare now 5 and 22. And put 5 in here. Next time, what should I do? Should I simply take 22 and put it in the output buffer? Or should I take something from here and put it into this input buffer? What should I do? Should I simply push 22 in here? Let's say this is A. Or should we take something from here and put it into this input buffer? This is B. Which operation should we do, A or B? Definitely B. Everyone said B. Excellent. If it is B, I'll remove all the data and ask you. So if it is B, you said that I need to take some data from here to the main memory. Which data I should take? From where? From R0 or from R1? From where should I take the data in here? From R0 or R1, or is it doesn't matter? 3 people answered and said 0. Someone said does not matter. Anyone else? Because main memory doesn't know the data, right? So that's why I removed that data so that you can't see which data is there. So now which one should I take? 2 people say it doesn't matter. 3 people say from 0. Another one say it doesn't matter. Both should be fine. R0 and R1 are equal. So you might misunderstood a little bit. It does matter. It does matter. If you take something from R1, then you are going to get wrong result. Let me show you one example. So think about what will happen if I take 23 and 24 and put it in here. Will that give me correct result? Definitely not. So if I put 23 and 24 in here, right? So what will happen? 23 will be compared with 22. and from there 22 will come up in here. And then since this is full, we'll push it into the main list. So that simply means after 5, in the main sorted list, we need to put 22, but that is not the case. In the result, I should have 7. Right? So after 5, it should be 7. So essentially what you are doing is that if you are taking something from R1, but you have some data in R1 in here, right? So you are comparing R1's data with R1, but that data is already sorted. Right? So we don't compare the data from the same list. We compare one list with another list. So when the first one is empty, right? So that simply means, sorry, when the first one is empty, that simply means that we need to take some data from the first block that we have. So in here, first one is empty, right? This one. So we need to take something from the R0 only, not from R1. Hopefully that part is making sense. So I take 7 and 11, right? 7 and 11 in here, I compare, 7 goes in here, we repeat that process then. 5 and 7 comes into here, then is another block. So 11 and 12, again compare, 11s come to the output buffer. We need to take 20 and 31, right? So we repeat that process and finally we'll get the final output. Does this part make sense, what I tried to explain? After this, I will give you a break. Okay. So this is known as external merge sort because we're doing the merge sort again and again using primary memory and disk. Okay, and that is the main thing that is written in here. Okay. So let me just go through all of this step at once. Where is the step? Yeah. So this part, first part is simply saying read B number of pages from disk to memory, sort them, okay, and write the sorted data back into the hard disk. Then merge is contiguous group, okay, and repeat that process. That's what I have just shown you. Select the first record among all the input buffer pages, write the record to the output buffer. If output is full, then write it back to the disk, okay. If the last record of the input buffer page, then read the next page. Someone is saying, how computer would know which one is the first block by index? So how it divided the whole thing, right? So if it divided that from memory 100 to memory 200 is my first block, that's what I can feed in the main memory. So that's how it will know. So that depends on how we divide this data. Right? Any question on external merge sort? So this is what you need to learn, okay, how external merge sort works. Not the merge sort one. Okay. If there is no question, we'll take a break of 5 minutes, then we'll talk about join algorithms. Someone is saying, if we input R1 in the first block, in the next step, we should input R1 again. So you are thinking that we'll put R1 in here and R0 in here at the first step. So yeah, so if this one becomes empty, then you need to take R0 in here. If this one becomes empty, then you need to take something from R1 to fill this one up. Right? So depending on from where you are getting the data, you need to get the data into the same block from the same position. Okay? Hopefully that makes sense. Yeah. Okay, so let's have a break. Then we'll talk about this join algorithm. Take a 5-minute break. We'll come back on 7:15, 15 past 7. Okay. In the meantime, if you have any question, write it in the chat box so that you don't forget. When I return, I will answer those. Okay, I'm back. Hopefully everyone is back too. Yeah, someone asked, little pieces can be sorted in memory. Then we sort these pieces using external merge. Yes, that's right. So whatever size we can fit into the main memory, we'll first sort that one into the main memory. Okay, and we'll repeat that process using external merge sort. Looks like no other question there. So let's move on to join algorithm. So you remember different kind of join operation that we have learned. Three sort of join. First one is theta join. Theta join simply means there will be a condition, right? So if the condition satisfies, then we will perform the join. Equijoin simply means that there will be equal relation. Okay, so if the specified attribute match in the value, okay. So in the equijoin, we always say the attribute name, right? So if those attributes match with one another, the value of those attributes, then we perform the join. Natural join, if all the attributes of same name and comparable type are there, so we'll try to combine all of those and then join. Right? So these three kind of join, hopefully you remember. Theta join, putting a condition. Equijoin, only equal condition will be checked. Natural join automatically checks for all the attributes with same name and compatible type. If they have the same name and same data type, then those two attributes will be matched. So how join works, or which sort of algorithm do we need to do? Okay, so that's what we are going to learn. First, think about, I have these two tables, assessment table and lecturer table. Okay, and I am performing this natural join. Can anyone tell me how many rows of data will be there in the resultant table, in the output table, if I perform natural join between these two tables? How many rows of data will be there in the output table? Yep. 3 people said 3. Any reasoning why it will be 3? So main thing is how natural join works, right? Why it will be 3? Any reasoning? Yep. So like someone said, we have 3 attributes in here, which we need to compare. So in here we have unit of static code. Here we also have unit of static code. Here we have same semester. Here we also have semester. Here we have year and year as well, right? So natural join checks for all the matching attribute where the name is same, data type is same. We can see the same data, right? So that's how natural join works. So we'll compare each of these row with each of these, right? So if something matches, we'll only get that one as output. So this will be the output, right? That will simply check whether this part matches with this part or not. If it matches, then that row will come up. If it doesn't match, we'll simply discard that. Hopefully that part is making sense. So in here, we know from join simply means that we'll take data from both the tables. So this part is coming from assessment table and this part is coming from lecturer table, right? Where we have some common attribute in here. How do we write that in relational algebra? You remember the symbol, right? So this symbol means natural join. So when we simply want to perform natural join, this is what we write. Join is very common, right? So most of the time when we write a query, we write more than one table name in from clause. So that simply means that we are joining. So that's why we want to learn how join algorithm should work. So in relational algebra, this is a symbol that we have used, and we have learned that this natural join is equivalent to performing Cartesian or cross product followed by a selection. Hopefully everyone remembers this equation that we have learned before, that R natural join S simply means R cross S, and then there will be some condition in here, theta. Hopefully everyone remembers this equation. We previously calculated as well, if you remember, which one have higher cost between these two. Let's say this one is A, this one is B. Which one will have higher cost? Does anyone remember? Simply think about how many rows of data we need to look for, right, for this condition. Someone said B. Anyone else? Which one have higher cost between these two, A and B side? Definitely B, right? So if you remember cross product, so if I have 1000 data in here and 200 data in A, so when you do a cross, so we will cross everything, right? So we will have 20,000 data, and from that 20,000 data, we will apply this condition and then try to figure out what will be the output, right? So definitely this one is much costly, right? In this table, if we have a look, here I have 4 data, here I have 3 data. So first of all, it will figure out 12 rows of data. And on that 12 rows of data, it will put that condition and finally figure out what should be the final output. But the main thing is it will create a larger table, right? So that larger table we need to create, and in that larger table, we need to select the data. Yeah, so that one is written here. R cross S is usually significantly larger than this one. Okay, so that's why this second part will be inefficient. Someone is asking, so if there is no same tuples at all, the natural join will output 12 for this example, right? Can anyone else answer? What do you think? Someone asked, if there is no same tuple, that simply means same row, the natural join, what the natural join will output? Yep, it should be nothing, right? If there is no matching data, we will not output anything. So we always try to match, right? So if there is no matching data, it should be nothing. Okay, so how should we implement these join operations, whatever join we are using? Okay, so 3 sort of techniques are there. First one is nested loop, next one is block nested loop, and last one is index nested loop. So index, you understand, we have created an index, and based on that, we want to perform the join. Block, we have the idea of block, right? So where we store the data, and nested is normal nested loop. If you are familiar with any programming language, you understand what does nested loop means. So nested loop means one inside another, right? So we have a loop inside another loop. So that's what nested loop means. So join will simply, so whenever we have a join, we have more than one table, right? So if we have 2 tables, we need to run at least 2 loop there. You can understand that. Take everything from the first table, take everything from the second table, and then try to perform join. So that's what the nested thing is there. If you are not familiar with nested, don't worry, we'll have a talk about that. So which one should we use among these 3 depending on the cost? So that's what we are going to estimate next. Okay, and we'll always choose the one with the smallest cost. Again, cost means number of IO. Which of these algorithms will require less number of input output? That's what we want to figure out. Okay. So as an example, let's think about some specific values. Okay, figure out some notations there. So R with this 2 bar. Okay, so this one will represent the tuples in R. How many tuples or how many row do we have in R? We'll represent using this symbol. BR simply means how many block we have. Since last week we assumed that each block means 1 page, so BR number of pages are there to store our table. Same thing for S, right? So this number of tuples are there, and we have this number of pages for that table. Okay. Let's think about in our example, R is a student table, S is an enrolled table, and we have this number of values. So number of students is 1000, number of enrolled information is 10,000. Number of pages we have to store all of this information, 100 students information, we need 100 page or 100 block. In enrolled table, we have 10,000 data to store all of those. We need, let's say, 400 pages. So that's what all the information we have. Based on that, we want to perform join. Okay, so this is natural join, you can see. So what should be the cost in these three algorithms that we have just seen? Okay, so we know how this one works, right? So how this one works, so we first take the first row from the first table and then compare that one with all of the rows, right? So that's what we do. So we start by taking one row, compare it with the first row, then we compare it with the second row, then we compare it with the third row, we compare it with the fourth row, right? So that's how we compare whether the values are same or not. So that's what we need to do. So that's what the first thing is, nested loop join. That's what nested loop join says. So nested loop join says for each tuple means each row R in BR. BR means in the page where I have the table R, right? And for each tuple S from BS, take one from here, and then compare, right? If the condition is true between R and S, then add it to the result. If you have idea about nested loop, then this part is very simple, right? So for each of these tuple in BR, you are taking each of the tuple from S, so that's how we'll compare everything. That's the simple thing, right? But to get access to the tuple, because we are trying to calculate the input output cost, so where are those tuples? So these tuples are actually in the block, that is actually in the page. So we need to read all of those pages, right? So for all of this tuple, we need to read all the pages. So again, all of this tuple, we need to get access. We need to read all of those pages that we have, right? And for reading these pages, we will need IO cost, right? Because the pages are stored in the secondary memory, we need to take them into main memory. So that's where the input output cost will be. In here, we can see that we have first used table R. So this table R is known as the outer table. S, which is inside the loop, is known as the inner table. Okay. What is the benefit of this technique? No indexes can be used for any kind of join operation. There is nothing in here. We are taking everything from R and comparing with everything with S. Right? So we can apply it for any technique. You can understand this is very expensive, right? Because we are checking every pair of tuples in the two tables, right? So we are comparing everything with the rows of other table. How much cost do I need? The number of IO, so we need to read all the pages, right? So how many pages I have? I have BR number of pages, so I need to transfer BR pages, first of all. And second of all, how many times I need to transfer BS number of pages? Only once? No, right? We are transferring these pages or BS, right? How many times, or how many times we are transferring from secondary memory to main memory? For each tuple of R, we are transferring each page of S, right? So that's what we can see. So what should be the cost? If you are familiar with loops, so you know that this one will be R multiplied by B of S. For each tuple, we have R number of tuple multiplied by, we have to transfer this BS number of pages for each of these tuple. So this will be the cost, transfer cost, right? So what will be the total cost? So for reading all of these first pages, we need BR. To read S, we need this amount of transfer. So in total, if we sum them up, right? So this number of transfer we need for nested loop join. Hopefully this part is making sense. So this one is simply saying for each tuple, transfer all of the block for S. And this one is simply saying only transfer all the blocks once for table R, right? So if we sum them up, we get total number of transfer we need. And that is the IO cost that we have. Again, in here, R means the outer table, S means the inner table. If we change that behavior, like if we put S as the outer table, R as the inner table, right? The equation will change. So that time it will be BS plus S into B of R. Hopefully you understand that part. So this was the information given to us. Simply, if we put it in here, this is what we get. If student is the outer table, right? So R means student table. At that time, this one will be the cost. If enrolled is the outer table, at that time, this one will be the cost, where S will be the outer table. So the equation will be BS plus S into BR, right? So like written in here. So if we simply put all the values from here in this equation, this is what we are going to get. So knowing in these two, which one we should use as an outer table? Which one we should use as an outer table? Any idea? Anyone can guess? Yep. Someone said that one. Which one have? Someone is asking, is outer table already defined or should we make decision? You have to make a decision which one will give you less IO cost, right? So that's what I'm asking. How do you make the decision? Yep. Everyone said R or student, right? Why? Because main thing is this R, right? So this part is the main thing. We need BS, BR, that's fine. Either we need R or we need S. So you can see we need BR, BS, BR, BS is there as well. Only is R or S, right? And we are multiplying. So if R is less than S, then this equation will be, you will give me better result, right? So whichever table that I'm trying to join, whichever table have less number of tuple, like someone said, you need to use that one as an outer table. Okay, hopefully that part is making sense. So whichever table has less number of tuple, based on that, you will make a decision and use that one as an outer table. So that is about nested loop join. Very simple, simply run 2 loops and that's it. Okay, so this is nested loop join. Someone looked into this code very carefully and figured out one thing, that we are essentially reading all of the pages, right, in here. So in this line, we are reading all the pages for R. In here, we are reading all the pages from S. So essentially, we are reading everything. Okay. So if we simply change the order, then since we know that we have to read everything, okay. So if we read them first simply means if we transfer them first and then perform all the operations, that simply means now we can see that that part has changed. That first we are reading all the pages. So first we are reading all the pages of BR and then reading all the pages of BS. We are first reading all of them. And then since I have all of the pages now, I can get access to all the tuple, right? And then perform the exact same operation that I had. So this one is known as block nested join. So first we read the block, okay, not based on the tuple. First we read everything, because from nested join we learned that we have to read all the blocks, right? So first read them first and then perform all the operations. What benefit that one will give me? So now you can see how many times do I need to read BS? For each block or each page, I need to read BS. Previously it was for each tuple, you need to read each page, right? So in here for each tuple, read each page. Now I have for each page of BR, read each page of BS. So now I have page instead of tuple. So that one would be much more cheaper, right? So this two again requires IO. How much IO do I need? We know for R we need BR, and from here we need BR multiplied by BS. Hopefully that part is making sense. So first line is saying for each page, so that one is BR. And for each page of S, we need BS. Since they are nested, how much we need? We have to multiply all of them, right? So now we have BR multiplied by BS. instead of number of tuple, so instead of number of row, number of block will always be less, right? So this is the estimated cost. We need BR and we need BR into BS. Now you can see in this equation, there is no number of tuple involved. So this one will definitely be lower than the nested loop we had previously, right? So here now we can see that we are simply using all the blocks, how many blocks I have, and always number of tuple will always be greater than number of block that I have, right? So that simply means this is always a smaller, much more smaller than this one. This block nested loop join will give me better result than nested loop join. And in here, we can see the same thing. Which one should we use at the outer table? We need to make a decision. So whichever have the lower number of block, we'll use that. Right. Hopefully making sense. Last was index. Index is pretty easy. So when we talked about index in B plus tree, there was a property of B plus tree, if anyone remembers. What is the cost from finding any node? Does anyone remember? How many comparison do I need in this tree, let's say? In this tree, how many comparison will I need always to find any node? If this is a B plus tree. Someone said log in, no? Yes. 3, someone said height, yep. So whatever the height is, right? If you are familiar with height or if you are familiar with level, how many level we have, okay? So that was the property of B plus tree, that the length from root to leaf will always be the same. For any node, the length from root, hopefully you remember this one is root and these last 4 are known as leaf, that will always be same, right? So where my node is, that will always be a constant, right? A fixed value. How many comparison do I need and how many we need to transfer? So that's what we are going to introduce in index nested loop join. If I have an index that I can use for answering a query, right? So based on index, I can figure out which page I need to transfer. And in that page, whatever tuple I have, I can compare with those. Right? So that's what we are doing for each page, for each tuple in BR, for each tuple S, which satisfies this index, right? Add the result in the output. Right? So that's what we are going to do. So again, this is only valid if we have an index available on the inner table join attribute. So whichever attribute we are looking for, if there is an index available based on that attribute, then only this join is applicable, right? If the index is not there, this join will not be applicable, right? So we understand that from join. So what will be the cost? Now we know how much we need to transfer from root to leaf, right? So these two parts will require IO. First part will take BR, and this part, how much do we need? We can figure that one out. But this time we need to read each of the tuple for each of the tuple in R, right? So what will be the cost? For first line, we need definitely BR. We need to transfer all of those. For each tuple, we need to read each tuple depending on the index that we have. So each tuple this time, right? So for each tuple in R, we need to multiply that with a constant value. What is this constant value? So constant value simply means index will return us that constant value, right? Because the length will always be same. So that's what is written here. Hopefully this part is making sense. Where C is the cost from traversing index and fetching all the matching S tuple from one tuple of S. Okay, and C is always fixed. We know B plus tree, that is the property, right? What is the height of the tree? From there we'll know what is C. Okay, so if this one comes into your exam, C will be given to you. Okay, what is the constant value that you will have, And based on that, we can calculate this equation. Hopefully making sense. If indexes are available on join attributes on RNAs, use the table with fewer tuples as the outer table. So which one we should use as the outer table, right? So which one have fewer tuples? You need to use that one as the outer table to get the output, right? Because we are multiplying R with C. If we have S into C, sorry, S into C. So depending on whichever is lower, you will get the lower number of cost, right? So now we have idea about these three loop algorithm, join algorithm, sorry. So we'll calculate all of these three, figure out which one gives me the lowest cost, and from there, the plan executor will execute that plan that we generate for them. Any question on these three join algorithm? Looks like none. So that's it for today. So today we learned about different sort of query evaluation plan, different sort of algorithm, and finally we learned about different join algorithm. Okay. Yep, someone is saying a little bit very confusing, have to study it more. Yep, so study it more. If you have any question, feel free to ask next week as well. No worries there. Do we have any example about index join? For the time being, I don't have any example, but simply think about the index tree, try to figure out where in the leaf node you have the actual data, and then you need to compare, right? So compare part is fine. Only thing is you need to figure out the data, where the data is. And that part we have covered last week, right? If you remember. So that is the thing. Someone asked this earlier, not sure. Will we get a practice quiz? So yep, someone asked that one and I already answered. But again, no, there will be no practice quiz for quiz 2. Is there any condition to use block nested loop join? No, there is no condition. That is simply the implementation issue, as you can see, right? So if you are actually implementing these two, how you are writing these loops, so that is the main thing, right? So you can use block nested loop anywhere. But good question. Okay, so that's it for everything that we have for this unit, not only for today, but for this unit. Okay, so next 2 weeks will be review. Next week, I'll review the content from week 1 to week 5, and then from week 13, we'll review the rest of the content. Okay, and someone asked me about final exam. Next week, we'll discuss about the final exam specifically. Okay, how much time will you have? How will you answer? That is quite different from the quizzes that you have seen. Okay, final exam will be something different. So we'll discuss about that. I will show you how you can prepare your document, how you need to submit, what sort of question you might expect in the final exam. Okay, so all of those things we will discuss next week. Someone asked me about final exam, so I will answer that one next week. Okay, so next week we'll have a discussion on the final exam. If you have any question, you can ask on week 13 as well. So next 2 weeks are revision. So come up with the questions that you have regarding any of the content that we'll have. Okay. Someone is saying, is there any other practice material would you recommend for quiz 2? Go through the lecture slide, that is the main thing, and also with the tutorial sheet. Okay, that one will be fine. In quiz, do we need to choose which nested loops join to use? Yeah, depending on the condition, depending on the question, right? If the question is asking, give us the best join algorithm, right? So definitely you need to compare these three. So run these three, the three equations that you have, put the value, simply check whichever gives you the minimum result, right? But the main thing is learn all of these. If you have any question, you have 2 weeks to ask. Okay, so next 2 weeks, you can ask any question that you have. that's it for today. If anyone have any other question, feel free to ask. If not, then take 10-minute break and then go to the tutorial if you have one today. Thank you, everyone. That's it for today. Someone is asking, so is this the last lesson to get new knowledge? Yes. Next week will be revision. Someone is saying, could you please re-upload this week's PPT? Yep, okay. I'll upload this one again. Yep. Someone is asking about final exam. That's what I said, right? So next 2 weeks, we will specifically talk about final exam. There I will answer your question, okay? Someone is saying, how do we need to download? What should we need to submit? I'll discuss specifically that next week, okay? I'll show you as well what you need to do. Someone is asking, do we all have the same exam questions? Like I say, it cannot just hold your thought for next week. Next week and week after that, I will answer all of the questions regarding final exam. Okay. Next 2 weeks are dedicated for final exam question. Someone is asking, so quiz 2 is next week? Yes. If you missed that part, at the beginning of this lecture, we discussed about that. Yep. So next week on Thursday, quiz will release after the tutorial, and the due date is on Friday. Looks like there is no other question. Thank you, everyone. See you next week.